forgot to bring your homeworks down, but I graded them and I put the grades on Coursera, so I'll give you back the homeworks for the next class. I've also put a new homework up on Coursera, which is due next Tuesday. Okay, so let's keep going with our discussion of different states of the electromagnetic field that we started discussing in the last class. So in the last class we introduced the Fock states. And the most general Fock state, for multi-mode Fock state, for example, is given by this generalization from the previous class for any state of the field based on the operators. So it's just a dagger acting on the vacuum for, say, the number of times in R, in the rth mode, and then divided by the appropriate normalization factors. It's a little cumbersome to write, as you can see. And that's the vacuum for all of the states. So it satisfies that, so this is the state that satisfies a, k, lambda, 0 equals 0 for all k lambda, right? So that is the vacuum. So this is a very highly cumbersome state, the multi-mode Fock state. Also are very difficult to create, even though this is the simplest to visualize in terms of the operator representation. Experimentally, these are the most difficult to create in the lab. We will quickly focus our attention on a single mode, like I mentioned last class. So instead of considering this multi-mode Fock state, this is multi-mode, we'll immediately go to the single mode case because it just makes the math less cumbersome. Okay, and so that is just very simply any n is a dagger n 0 square root n factorial, and a dagger a n is just, I wrote all this last time, but I'm just repeating it one more time. And n is equal to a dagger a is the photon number operator. And we also have the electric field for this single mode. And this is one polarization as well, is implied in this. I didn't have any polarization right now. Okay. And somebody asked me after the class, like, what if it's not a single mode, single frequency? How do you write this thing? And so one of the ways you could, for example, write some, say, a pulse in time or a localized wave packet. We'll also see how to do this more with coherent states, but it's clearly you can write some summation over some small frequency range. If you have some small frequency range for the thing, you could write a omega e to the I k dot r minus omega t, right, plus Hermitian conjugate, and then this would represent some kind of electric field that is a superposition of a few frequency modes, and then you could work with a new operator. For example, in the time domain, that's just the summation over omega, a omega e to the minus I omega t. That would be a of t, which represents some small pulse in, say, a time domain, for example. But you have to be careful because this probably only works best for something that doesn't have huge set of modes. Because of course, if you have to worry about dispersion of k with omega and stuff like that, then you might have a very different looking state. So we will stick to the single moded case because that is a pure quantum optics case. But as I said, you can try to come up with operators. Then usually what it all has to do also depends on the detection process, as we will see in a minute. Like so, if your detector is only sensitive to some narrow range of modes or a certain set of modes, then you can try to write some annihilation operators that are specific to that particular set of modes, and that's more typically how you would try to simulate, let's say, some experimental result, is by thinking about what set of modes actually plays a role in your experiment, which is just standard physics, right? Which is, in any problem, we first try to figure out what modes are relevant for our problem, okay? We don't consider all the modes of the universe. We focus down to the modes, the relevant modes, and then we might try to come up with some operators that represent those modes, and then you can maybe think about number operators in that basis. But as I said, you have to be careful about dispersion, because if you have more than one frequency in the problem, then then of course the various operators are going to get out of phase with each other. So you have to keep track of that phase relationship and stuff like that. But that's just standard quantum mechanics. So if you want to work in the time domain instead of the frequency domain, you make this Fourier transformation, and that will help you to think about operators in the time domain rather than the frequency domain. But we are working in the k and omega space, so to speak. Okay. Was that clear? The sort of idea? Okay. So we have the Hamiltonian for this system now. It's just h bar omega n plus half is the operator that for the Hamiltonian for the system, and so that's a Fock state. Theoretically, these are the easiest states to write, and they are they're a good sort of eigenbasis for other things. So the next type of state that we will generate, which was historically in physics, and the thermal states of light were pretty much the only states that were available till the invention of something like the laser, right? Because before we had a laser, people took like various things, obviously sunlight, but also like bulbs and discharge lamps, and so until about like the 1950s or so, or 1960s, when finally the laser was invented, we didn't really have a strong, coherent source of light for optical fields. And even for, say, microwaves, microwave generators were only invented, say, in the 1940s and 50s. So it really, has been a very recent development that there is anything more than thermal states of light. So let's consider thermal states of light. And so for a first principles derivation of what the thermal states of light should be, I refer you to Meister and Sargent, page 304 to 305 in your edition that's available online. But without too much ado, without proving the result, I'll just write down. So since it's a thermal state of light, we know, remember I explained in the last class that you can have different states which are pure states. So a Fock state is a pure state, right? Because it is definitely a state which does not have different probabilities to be in the various number states, right? So you can write a wave function that consists purely of the Fock states, has some superposition, and that would be describing the state ket of the system. In a thermal state, by contrast, we don't know which number state we have prepared the system in. There's a probability to be in different number states, but we don't know anything more than that because it's a thermal distribution, right? And so the correct description for a thermal state is to use the density operator. Okay? And the density operator for a general system, which is what is proved in Meister and Sargent, is simply, this is a result from quantum statistical physics, if you like. You might have seen it in other cases, is that you simply take the Hamiltonian and raise it by an exponential, divide by kBt at some finite temperature. It's thermal, so it has a temperature that characterizes the state, right? And then you divide by the trace of that to normalize the system. Okay? So this should look like a Boltzmann distribution, right? And in fact, as soon as you write the system as a matrix, you see immediately that it is indeed a Boltzmann distribution, because in the Fock basis, right? As I said, the Fock basis is a nice basis in which we can write down different states of light. In the Fock basis, because H is diagonal in the Fock basis, e to the minus h over kBt is simply summation over n e to the minus n h bar omega over kBt times the operator for each state n. Right? So this is a matrix, right? And this matrix essentially on the diagonals has e to the minus n h bar omega over kBt, which looks just like what you'd expect from a Boltzmann distribution. Each state has a probability to be populated, and the probability to be in that particular state is simply e to the minus the energy divided by kBt. Okay? So hopefully that's that is acceptable. I'm not proving the result that the density operator for a thermal system can be written like this. You can look at Meister and Sargent for the more detailed derivation. Okay? But I think this is pretty intuitive for most of you guys. So the density, the thermal density operator then, so then of course you have to still calculate the trace of this matrix, which is easy to do with the geometric series, right? Because this will just be a geometric series, 1 plus e to the minus h bar omega over kt plus e to the minus 2h bar omega kt, etc. So you'll get in the denominator 1 minus, well actually, so after doing the derivation you can write 1 minus e to h bar omega, minus h bar omega over kT times summation over n e to the minus n h bar omega over kT times. So that just comes from normalization carrying out the trace of this matrix. Okay? And then we can also calculate the average value of n is simply 1 over e to the h bar omega over kt minus 1. So just the Planck distribution for thermal modes, for thermal light. You can also see, because E, the operator for E, the electric field in a single mode, has an A dagger in it, you can easily show, because this guy is diagonal in n, the number state basis, you immediately see that in a thermal state, the expectation, right, for this guy is 0, right? Because of this. And also it's obviously, I should have mentioned, the expectation for E, the electric field in any one of the number states is 0, right? Even if you had, say, not a thermal state but a Fock state of state n, then the expectation for E, the electric field, is 0. Okay? Which means, and because of that fact, you can easily show that trace of rho E, where rho is our thermal state over here, is also 0, right? Because this guy is also diagonal in the number states, so the trace of that with the electric field, which is always going to be off diagonal, is going to be 0. Okay. So A and A dagger means that the electric field always has only off-diagonal components, has no diagonal components. So the density matrix, the trace of the density matrix. Remember, when in the last class we discussed that the expectation of any operator is simply the trace of rho times that operator. Okay. So because of that, this already tells you that Fock states cannot be states where there's any average amplitude to have an electric field, which is of course what we want when we are thinking about a classical state of light. Okay? But any Fock state and any thermal state both have the average expectation value of the electric field to be 0. Okay? But of course there are fluctuations. Okay? And that's what we typically observe in these states, fluctuations around the mean value. Okay? Okay, now in fact let's quantify those fluctuations. So we already wrote down n the average value, which is just that number. We can similarly write down n squared, okay, which is the variance, okay, and you can show that that is simply 2n squared plus n, okay. Again, that's obtained by taking the trace of that with the density matrix or by doing it any other way you like to find n squared. Then, which implies that the standard deviation or the variance sigma n squared, which is of course just expectation of n squared minus n the whole squared, right? That guy is simply n squared average of n squared plus average of n, or you can write it as, you may see this as n times average of n plus 1, or sometimes people write it as n bar times n bar plus 1, right? N bar again representing the average value. Okay. So again, I'm not proving any of these results. They're fairly simple once you put in those operators and find the trace and so on. So we'll just discuss sort of what these mean. Okay, so here, for example, we already have our first example of what I call super Poissonian statistics. Because you can see that the fluctuations, the variance, sigma n squared, is not equal to just n bar. Remember, for a Poisson distribution, which I proved without, I stated without proof, but you should all be familiar, this sigma n squared is always equal to n bar, right? Or the standard deviation is equal to square root of n bar. Okay, which is just taking the square root on both sides. So this is a super Poissonian statistics. So sunlight, the light from some kind of discharge lamp, which if you take it and filter it into a narrow mode, then of course you should expect to see super Poissonian statistics. But here is something that you might have noticed. It doesn't feel like the light coming from sunlight or from a discharge lamp or a tube light is flickering a lot. It feels fairly steady with probably some fluctuation. So if you put it on a photodetector and looked at it, yeah, there are fluctuations. It doesn't seem like it's going up and down crazily, right? Like this guy would imply it should go as n bar squared. Like as n bar gets large, this should be going as n bar squared, not n bar, right? That's what our super Poissonian statistics is saying. Oh, by the way, I should have sort of just briefly, if you look at the density matrix, right? I forgot to say this. This is the density matrix, right? So if you look at the probability to be in any state n, right? Probability to be in a state n for a thermal distribution, you find that the thermal distribution is peaked around 0. Okay? So for example, if you compare a thermal distribution with n bar, say 10, okay, right? You find that the peak is at 0, and you find, of course, for a Poisson distribution, the peak is going to be somewhere at n bar equal to 10. right? This is Poisson, and this is thermal. Okay, so I'm just sketching it. You can easily put those into the computer and see for yourself. So you see that there's a very different looking distributions for thermal and Poisson. Okay, just from looking at that, right? Because it's an exponential with n. Okay, ignoring the normalizing factor, you can immediately see this. So the peak value is at n equal to 0 for a thermal state. Okay, but what I'm saying is that the statistics the spread n sigma n squared is greater than that for a Poisson distribution. Okay, especially as n bar gets large, this guy is going to have much bigger spread. Okay, because it goes as n bar squared. The dominant term here is this n bar squared over the n bar itself. So what's going on? Why is it that when we look at sunlight, a thermal state, for example, we don't see this kind of crazy super Poissonian statistics all the time? And this is where, for example, I told you guys, okay, first of all, any guesses? Why don't we see lots of fluctuations, big distributions with sunlight, for example, just regular sunlight that we're observing, or from a lamp, and so on? You look at the light from the sun, it's fairly steady, right? Of course, there's change with the day and so on, but any small instant of time, it doesn't fluctuate widely with n bar. If you were to observe the statistics of it, seems fairly almost, if you look at it, fairly constant with some fluctuations around the mean value. If you have ever done this experiment, you may not have. But maybe you worked with arc lamps in the lab, right? When you did optics labs, you might have taken a neon lamp, or you might have taken some other lamp, mercury lamp, whatever, and taken that and put it on a photodetector, for example. If you observed it, it didn't look very crazy, I'm sure. It had some if you do that experiment, it's fairly straightforward, right? Take a photodetector. This is how a lot of photodetectors work that are used for lots of things around when you walk into a room and the lights go on and off, they're sensing basically levels of light and motion and so on. Or you might walk into an elevator and it cuts the beam, whatever. Many of these situations, it seems like the statistics are not so crazy as to trigger events. And the reason for that, if you haven't heard any guesses, still anyone want to guess why this may be? That the light from a lamp or from a thermal discharge lamp or from sunlight is not crazy?
I guess because there are many atoms that are emitting.
Many atoms that are emitting. Close, you're getting close. It is many, but many what?
They're emitting at different times.
They're emitting at different times, so they don't have any coherence between them. Very good. Which also means, well, you're getting close. So the idea is that in fact when we normally look at sunlight, we're looking at many modes of the field. We are not looking at just a single mode. Making a single mode means you have to narrow down the frequency range substantially, right? Which is kind of what you were saying. We are looking at many different atoms or many different types of emissions all happening uncorrelated fashion. And uncorrelated is actually very important for this next step that I'm going to show you. Okay, so let's consider n electromagnetic modes, which are all in a thermal state, and they are uncorrelated, like she just said. So what is the total photon number, right, is simply the sum of the individual numbers. N times n bar, or if I don't want to write that, I'll just write this. Okay, that's clear. And what is sigma total square? This variance. This is the key, right? if you have n independent modes, each of which has some variance sigma n, okay, and they're all in some band of frequencies, but still they are uncorrelated with each other, then the total variance is equal to you have n modes all uncorrelated with each other. The variance of the modes should be equal to the what's the relation to the variance of each individual mode? You know this from like probability, other random processes. Yes? Sigma over. This is sigma n squared over n. Sorry? Huh? You're not sure? If you have n random variables, or if I toss 10 coins, okay, and I know the probability for each coin to land heads or tails is half, right? Then what is the probability of, you know, of the 10 coins, for example, or let's put it this way, I guess I'm coming up with coins, but I should come up with something a little bit more. Well, maybe the coins is fine. So if I have 10 coins and I toss them up, right, and you know that the mean value will still be 5 for the number of heads, right? And but then what is the variance of that distribution? Okay, if I know the variance of one coin being away from, you know, the value for one coin to be away from this average value, and I have n such independent coins, then I should add up all of the individual variances. So if I have xi being independent random variables, then the average value, right, is simply sum over I xi, right, and the variance sigma squared is the sum over I sigma I squared for n independent random variables. So this guy is also sigma n squared. So this we can now write as n times n bar times n bar plus 1 from that earlier result, and now I divide or I want to express this in terms of n total bar, which is the average value of that guy, which you can clearly see will go as this is n times n bar, so you'll get essentially it implies that sigma total squared is equal to n total bar plus n total bar divided by n. Okay? So, as n goes to larger, the capital N I mean, this goes to 0. Okay, so as we have n independent uncorrelated modes, the total, the variance approaches that for a Poisson distribution. Okay. Maybe let me see if that makes a mistake. No, I think that's it. Okay, anyway, we can figure it out if I made a mistake. It's definitely of this form. Maybe I'm missing some squares there somewhere. Okay. So the idea is that that last term will have 1 over n in it, and that will go away to 0. So the point of this is that when you have n independent modes, even though each individual mode, this is actually like central limit theorem in some way, right? You know the central limit theorem, right? If you have n independent observables, right, errors, for example, with some different statistics, and all the statistics are different. Like one guy could be following Poisson, another guy could be following exponential, another guy could be following Cauchy distribution. Each error in your experiment could have some distribution that you don't understand. But as long as the distributions, each of those errors or distributions is independent of the other ones, and they have some small value, they're not like huge, then, and you add up all of them, right? That's another important thing, you have to add up all the errors. In that sense, then the total distribution will always tend to a Gaussian. And this is a similar result except for light, which says that if you have n independent thermal modes, they will add up, the fluctuations will become more and more Poissonian as you add them. Okay, I'm going to stop with that and move on. Okay, if you have more thoughts or questions, we can discuss that later. Okay, so we have discussed the thermal modes. Now I want to move on to the next type of state, which is coherent states. Sorry, now I'm a little bit bugged. Sorry, I have to figure it out. N total bar squared is n squared n bar squared, right? And this guy here is n times n bar squared plus n bar, right? So, huh? Sorry, I'm just making sure I got this right for you guys. I was confident earlier, but now I'm not so sure. So when I want to write this in terms of n total, this part is clearly n total, right? This is n total bar. Yes, so it's correct. So this is actually, sorry, this should be n total squared bar squared divided by, okay? So this part here, which is n times n bar squared, is n total squared divided by capital N, because there's a missing n over here, because n total squared is n squared. Okay, I got it right except for the square. The point is, once n is large, that guy is going to dominate and go to 0. Good, okay. I should fix my notes. Okay, good. Always good when I figure out my algebraic mistakes. Now we'll move to another type of state, which is called the coherent state. And remember, as we discussed earlier, the expectation value for the electric field in a Fock state and a thermal state is 0. So obviously what we want to do is generate states whose expectation value for the electric field is non-zero. Okay? So we want psi in this so-called coherent state that I'm calling, or a classical state if you like, for the expectation of the operator E will give me back E, the electric field. Okay? We want this. We want this. Okay? And we know E, if you go back and look, goes as some A plus A dash, right? With some E to the minus I and so on. But essentially it's off diagonal in the Fock basis. Okay? So we want these guys to have some value is non-zero. Okay? Which means we look for this motivates that we should look for eigenstates of A. And I'll call those eigenstates as alpha and have and have an eigenvalue alpha. Okay? And then clearly these states will have a non-zero expectation value. Now this is just obviously a very intuitive and physical picture. I have not proven anything here. So if you again, I refer you to Meister and Sargent. Pages 308 to 309 for rigorous proof. That is, they prove that A acting on alpha is equal to alpha times alpha. Okay. When you have a state that has a non-zero expectation for E. But as I mentioned a lot of times in this course, we just want to understand the important physics, and some of the mathematical details we'll skip. Okay, so now let's take the expectation for the electric field in the state alpha, okay, that I just defined over there to be the eigenstate of the annihilation operator A. Okay. By the way, you can ask the question, why don't I define it as a state A dagger? Okay, why don't I define an eigenstate of A dagger to be the coherent state, and you can actually show that A dagger does not have an eigenstate. Okay, so that's why we define this A acting on alpha to be the eigenstate. Okay. Okay. So if to find this, we substitute the definition. Okay, just a couple of steps. So pretty straightforward. I'll just put that in. U di A dot R minus omega t. And because A acting on alpha is alpha, we also have alpha from the left acting on A dagger, okay, to be just A acting on alpha, the whole dagger, which is simply alpha star times alpha. Okay? When you take the Hermitian adjunct. Okay? So putting all this in, so when I evaluate, I can use that part. So alpha from the left acting on A dagger is alpha star alpha, and with the bra, and then A acting on alpha gives me the expectation of alpha. So we get that this is simply square root h bar omega over 2 epsilon naught v times alpha e to the I k dot r e plus alpha star e to the minus I k dot r. And since alpha is a complex number, essentially what we have done is we've defined the coherent state such that it characterizes the amplitude of the electric field, right? Clearly, alpha, the eigenvalue, is characterizing the amplitude of the electric field in this mode that we have. So oftentimes you see later on when we do Hamiltonians involving single mode fields and so on, sometimes when we don't want to consider the quantized property of the field, we just want to consider the classical properties of the field, we'll replace A, the annihilation operator, by alpha, and A dagger, the creation operator, by alpha star. And we'll say that that means that we are essentially making the quantum field into a classical field, and that's where this comes from. This comes from this sort of, understanding that when you have a classical field, the A and A dagger guys can be almost the same as alpha and alpha star, the amplitude of the electric field. Okay, so these represent amplitudes of the electric field. So that's the physical now meaning of alpha, which is the eigens, which we, as I said, is just an eigenvalue for A, but now we see it also represents the amplitude of the electric field in that mode. Okay, and it's a complex number. So we can also look at something else which is interesting, which let's see. Because we wrote this in terms of alpha e to the I k dot r, alpha star e to the minus I k dot r, you can also see I could have recombined that in terms of cosines and sines. Right? I'll get an alpha plus alpha star, alpha minus alpha star, and then I'll have cosines and sines. But alpha plus alpha star, if you look at it, is simply, again, A plus A dagger. So this motivates defining two new operators, which are not that new. We have encountered them before. We call them the quadrature components. So I'll just define them over here, and then we'll just derive them over there, which is x is equal to half A plus A dagger, and P, which is half minus IA plus IA dagger. Now, I should emphasize something very important here, which is that this definition is just the convention that is being used in Scully and Zubairi and Meister and Sargent. Okay? Those are the two textbooks that I mentioned to you in the class. But there are many conventions for this phase over here. Okay? And in fact, the phase itself is not important, as I'll just show you in a second. What I mean by that is taking this minus I and plus I over here, the way I have done, right? Which is basically, you can also write this as 1 over 2I A minus A dagger, right? That's basically what this is, right? So, many other conventions exist. Okay, there are at least 3 different ways of writing this in various textbooks. Okay, but this is the convention used in Meister and Sargent, page 410. Also Scully and Zubairi, which is the other textbook I mentioned to you guys. I don't remember, I think it's page 61 or something. So that's what I have in the notes. So that's the convention that we have used for the quadrature components of the electric field. Okay? When you put these back into the definition for E, right, which is over there, it's pretty simple that E, now the electric field, can be written in terms of these quadrature components. Okay, it's x plus IP to the I k dot r minus omega t plus x minus IP and then we can rewrite all that. We may have to take out a factor of 2 over here, which makes this factor change. So it goes from here to here. Once I put in the factors of 2 for x and x dagger, or x plus IP, basically just combining these. So you get x times a cosine k dot r minus omega t plus p, minus p times sine k dot r minus omega. Okay? Because x multiplies e to the I k dot r and e to the minus I k dot r. So to write it in terms of cosine, I'll get a factor of 2 that comes out. Okay? And that gives me a factor of square root of 2 of k. Okay? So now we can see why I called x and p the quadrature components, because x is sitting in front of a term that goes as cosine, p is sitting in front of a term that goes out of phase by pi over 2, which is the quadrature, right? This is just a, if you're not familiar, some of you, quadrature represents two variables that are 90 degrees out of phase, okay? So cosine and sine are clearly 90 degrees out of phase, okay? And so that is a representation. You might also see this if you have done any microwave engineering. You may call these I and Q of the microwave modulations, modulators and things like that. They're the same. They mean the same thing. They are just 90 degrees out of phase with each other. Okay. All right. And obviously, it's pretty simple to verify that this x and p, they satisfy a different commutation relation, right? Just put that in. We'll just write the steps: a plus a dagger, a minus a dagger, right? Because I pulled the I sign out because it's sitting in front of the 1 over 2i. I make that minus I and bring it out, and then you can easily show that this is just I over 2. Okay? You have a and a, that vanishes, a dagger and a dagger vanishes, and then you have a and a dagger, which is 1, and then a dagger and a is minus 1, and so you get this I over 2. Okay? Okay, and when in the very first or second class, we said that whenever two operators have a certain commutation relation, the Heisenberg uncertainty principle or a Heisenberg uncertainty relation says that their variances, right, which is delta x and delta p, will satisfy this, this relation for the commutations. Right? This is the Heisenberg uncertainty relation, which comes about from the commutators, and that is going to be now from this is simply 1 over 4. So what we see is that delta x and delta p, their uncertainties or variances always have to satisfy this relationship greater than or equal to 1 over 4 for any state, coherent or otherwise. Because we didn't specify a state when we derived all this. Okay? Okay. Hopefully this is all fairly simple. So that's our quadrature representation, and what I can let me see this later. You can also kind of see that the phase of alpha. Okay, let me write this down. There's another interpretation of the quadrature components, which is that I just defined them in general here, but now I can put them in for this coherent state that I had just written them, which originally motivated the definition of the quadrature operators. And when I do that, you will immediately see that x and p will be related to the real and imaginary parts of alpha. Okay? So that's pretty straightforward. So instead of evaluating the electric field operator, now I evaluate the quadrature operator in the states alpha. Okay? So alpha x alpha is going to give me, because of the definition, is half alpha plus alpha star, which is simply a real part of alpha, and alpha is going to be 1 over 2 I alpha star minus I alpha, which is just the imaginary part of alpha. Okay. So now we have another interpretation for x and p, which is that they are so the first interpretation was that they are the quadrature components of a traveling wave, right? Of a traveling wave mode. And now this other, or the quadrature representation of a traveling wave mode. And the other interpretation is that they're in a coherent state, at least, x and p will be the real and imaginary parts of that alpha, which represents the eigenvalue of the coherence state. And now we can calculate the uncertainty delta x in a coherence state. So this is just real and imaginary parts are equivalent to the quadratures. In a coherent state. And the uncertainty delta x, to evaluate that, of course, I need to evaluate first x squared, right? Because that's what the uncertainty comes from, x, the fluctuations. Okay, so just run through that math, pretty straightforward. You put in alpha a plus a dagger, and a plus a dagger acting on alpha, right? And now that we have to write out a squared plus a dagger squared plus a dagger a plus a dagger acting on alpha. Okay. So a squared, I can operate it on alpha, that gives me alpha squared, right? So that's just alpha squared. Then a dagger squared, I can operate it on this alpha from the left, that gives me alpha squared. Okay. And then I can do the same thing, a dagger acting on alpha from this side, a acting on alpha from that side, I get alpha star alpha. Okay, and an AA dagger, I use the commutation relation, is just 1 plus a dagger a. Okay, so that's going to give me another 2 alpha star alpha, another alpha star alpha plus a 1, and so that's our expectation value for the for x squared, which you can easily show is the same as expectation value of x, the whole square plus 1/4. Okay. So the variance delta x squared, so this implies the variance delta x squared, right? Expectation in the coherent state alpha is simply 1/4, right? Because you just subtract off the expectation x squared, so that's going to give me the variance, so all I'll be left with is 1/4. Similarly, you can show delta p squared in this is also 1/4. Okay? Which gives us that if I take the square root, that for all coherent states, delta x for a coherent state is 1/2, and delta p for a coherent state is 1/2. So this guy satisfies that minimum uncertainty product, delta x, delta p is 1/4. Okay? So this is the most, the minimum uncertainty we could expect for a classical light field that has a well-defined value E, right? Or alpha in this case. You have a question? You look a little puzzled, sir. Is there something that I'm skipping or? You're good, okay. Everyone good with this? As I said, I skipped this, but you should probably verify for yourself with the same technique that delta p squared is also 1/4. Okay? That's a good thing to verify on your own to make sure you are comfortable with the matter. And maybe you've already seen this, I don't know. in some other, for harmonic oscillator or something like that, because the math is very similar. Okay, so now with this sort of, mathematical thing, it's always good to also have a spatial or visual representation of these states and of these quadrature components. So let's consider the electric field E at some position r equal to 0, and sometime t we just wrote down what it is in terms of these quadrature components. It's simply x cosine omega t plus p sine, or maybe minus p, minus p sine omega t in a coherent state, in the state alpha.
Sorry, excuse me.
Yeah.
I'm confused. So I'm confused about the notation here. So
Yeah.
when we write like delta x squared
Yeah.
in the expectation value of delta x squared, you mean the expectation value of the delta x squared? I mean, why the squared?
Oh, okay. So I have to go back and probably define for you that. Okay. That is the definition of the variance.
Okay.
Okay. So then to find delta x, you take the square root of this. So delta x expectation is square root delta x squared expectation.
Oh, I see. Yeah. Sorry.
Good. It's good to ask these questions. Yes. Okay. Where was I? Yes. So we wrote down E, the electric field. In general, it's just this. But in a coherent state, we know that these x and p become the real and imaginary parts of the alpha, right? So in the coherent state, so if I take this and apply it to a coherent state, I'm going to represent that along the x and p axes. Okay. What this says is that, of course, it has some mean value whose x coordinate is the real part of alpha. The y coordinate is the imaginary part of alpha, right? We just proved that over there, right? That the quadrature component of x in the state alpha is the real part and the other one is the imaginary part. Okay? And in this representation, essentially what I'm doing is I am moving with the electric field at the frequency omega, right? So you can imagine transforming to a frame at some time t, or imagine that you're freezing it at some time t, okay? At some time t, these guys, say cosine and sine, have some values, right? And this guy then represents the real and imaginary parts of x of the electric field, or this is the equivalent phase space representation of the electric field. Phase space representation, quadrature representation, IQ representation, all these are different terms that are used for writing the electric field in this way. Okay? And we also just derived that the field has an uncertainty, right? Which is denoted by the shaded region. Okay? Delta x and delta p, we know in fact that delta x is, if I write it on this guy, delta x is equal to 1/2, and similarly the uncertainty is equal, delta p, the variance in this is also 1/2. Okay? Also, since we are in this plane, this complex plane where x and p represent the real and imaginary parts of alpha, we can also write the magnitude of this value, which is the magnitude of the alpha, represents the point, real and imaginary parts in x and y direction, also can be represented in the polar coordinate as alpha and some phase phi, right? So alpha can be written as we just saw as either the real part of alpha plus I times the imaginary part of alpha, which is equivalent to x plus IP, right, as we just showed, and is also equivalent to the magnitude of alpha times the phase, or e to the I phase, right? All of these are equivalent ways of writing the state alpha, okay, the eigenvalue alpha. And this phase phi, as you can see, we erased it, but when we wrote down, or if we put it back here, for example, right, you can see that by putting this back here for alpha and writing this out, you see that this phase phi represents e to the I omega t plus phi, for example, or e to the minus I omega t plus phi. When you write this, when you put this back in this expression for the electric field, so this phase phi is the equivalent of the phase of a classical field that we wanted to get to at the very beginning of the course when I was talking about there are two things that define a classical field, the amplitude and the phase. And now we see that the phase of a classical state of light or a coherent state of light in terms of the phase of this alpha, the complex number, which is the eigenvalue of the operator A, represents the phase of a classical laser field. Okay? So you can think about the phase, of course this is in a frame that's rotating with the same frequency omega with the state, with the electric field. We have essentially removed all that time dependence, but you could imagine if you let time progress, then the state is going to rotate in time, right? It's going to oscillate. In fact, in this case, it will oscillate clockwise, or not oscillate, but rotate clockwise, because as time progresses, the phase basically decreases, right? P starts to go down, and you'll just keep it rotating in a clockwise fashion. That just is a consequence of that original convention I chose for x and p. That x, the way I wrote x and p, and that can be changed simply by changing that convention. Okay, in fact, as we'll see, this phase is, pretty easy to adjust, so to speak, to what you want. Okay. So of course we know how to measure the amplitude of an electric field, right? It's pretty straightforward. We just put it on a photodetector, and then we can measure its amplitude. But measuring the phase is a little bit harder, right? It's always harder for electric fields. Well, microwave people have no problem, okay? They have mixers to do that for them. But laser people, we all know it's difficult to measure the phase of an electric field. And so we had to resort to some tricks in the optical domain to measure the phase of the electric field. So it's easy to measure the amplitude, harder to measure the phase for optical fields. In the microwave domain, it's easy to measure both because there happen to be elements that are very easy to fabricate in the microwave domain compared to the optical domain. Okay? And the trick, as I'll explain in a bit, is to use something called balanced homodyne detection. Okay? What we do is essentially we mix the state, we mix the field that we want to measure with a stable field with a fixed frequency, which is called a local oscillator. Okay? We mix it and we put it on a beam splitter and two detectors, and then by measuring the photocurrents coming out of the two detectors, we can measure both the amplitude and the phase simultaneously. Okay? So I've just given you, I've not proven any of these statements, but I'm just telling you if you're curious how to do it, then balanced homodyne detection is the typical way, or that is basically you measure the field by mixing it with a local oscillator. And mixing in the microwave domain is much easier. There are mixers that are available. So you just buy a mixer, you put the incoming microwave field that you want to measure, and you put a local oscillator, which is just a signal generator. You put that in the other port, and the output will come out to be proportional to the amplitude and the phase of the microwave. Okay, so that's the easy part with microwaves. as I said, in optical domain, balanced homodyne detection is the way in which we accomplish the same thing, and it's a little harder to set up, but it's still doable. Okay. We can also see that the uncertainty relation, right, is going to imply that you cannot measure both quadratures of the field with high precision simultaneously, right? As we can clearly see because of this uncertainty block that is there in this coherent state. Okay. So that is the equivalent sort of uncertainty principle for electromagnetic field in this. Okay. Okay. How much time? Okay, a few more minutes. So the final thing I want to do is, besides these representations, we of course want to go back to the Fox state representation and understand what the photon statistics are in a coherence unit. Right? Remember, we started by writing the photon statistics for a number state. For a number state, it's straightforward. There's a peak at n equal to the value of the number state. Right? For a thermal state, I showed you that the photon statistics is this exponential distribution, and now we want to show you, there's no secret here, that the coherent state will have the Poisson statistics that we have always said was a representation of classical light. So that is pretty straightforward to show because we have the eigenstate alpha as an eigenstate of the annihilation operator. So we want to write it in terms of some amplitude alpha in the state n, right? That's the component of alpha along the Fox state n, and so this is just a representation of alpha in a new basis. Basically, we are transforming basis from alpha to state n, and then we just write this expression for the number state. Each number state is represented as the from the left. So of course, any number state, I already wrote this down, is a dagger to the n acting on the state 0 divided by square root n factorial. And now I have to take that from the left, from the bra side. So that's just the same thing written with a acting on n. And of course, a acting on alpha is simply alpha. So this just becomes summation over n, 0 alpha times alpha to the n divided by square root n factorial acting on the state n. Okay. And so the only term that's unknown is this component of alpha, which is projected out to the state 0. So what is it? So well, we would like so what is this? We would like the normalization that alpha is equal to 1. Okay. So then substitute all of these terms back into this expression for alpha. So that's just sum over n prime, alpha star to the n prime divided by n square root of n prime factorial, alpha to the n square root n factorial. Right? I am writing out alpha in terms of this same expansion that I just wrote down. Then I have n prime on n, and then I have 0 alpha times alpha 0. Okay, and that's the term that I want to obtain. So this guy is going to be delta n prime n, and that will make these guys into alpha to the 2n, and this is the normalization factor 0 alpha whole squared that I want to determine, and from all of this you can, and I'm equating that all to 1, so I get summation over n alpha to the 2n divided by n factorial, and then 0 alpha squared, right, is equal to 1. and this summation of n alpha to the 2n divided by n factorial is simply the exponential 2 alpha squared. Sorry, I ran out of space, so let me move on to that. Okay, I missed. So this is the same as e to the modulo alpha squared times 0 alpha squared, and that I'm equating to 1, so we get 0 alpha is equal to e to the minus alpha squared. Okay. So now we know what that 0 alpha is, the component of alpha along the vacuum. Okay. It's just square root of this. Okay. So now we have the photon statistics to be in the nth number state. Erasing this. So the probability to be in the nth number state is simply projection of alpha onto n whole squared, which from this derivation simply e to the minus alpha squared times alpha to the 2n divided by n factorial. And this is indeed a Poisson distribution. With mean of n, which is equal to alpha squared, and therefore the variance delta n squared, which you can verify, is also equal to n, is also equal to alpha squared. Okay? So that is now the proof, or the final sort of, we are closing that loop, showing that we have now derived all the different types of statistics, right? So the Fock state has sub-Poissonian statistics, right? Clearly, if a system is in a Fock state, then it has well-defined number, say n equal to something, whatever it is, say 10, and then its variance is 0. So that's super, it's extremely sub-Poissonian because its variance is 0. There is no uncertainty in the variance of the number state. We then saw the thermal state, which has super Poissonian statistics, right, for a single mode, and then as you add up many modes, it approaches Poisson statistics. And now we have the coherent state, which has, for a single mode, has Poisson statistics, and you can ask yourself what happens if it has more than one mode. Okay, and that I'll leave as sort of investigation for you guys to think about. If you have more than one coherent state, or more than one mode that's in a coherent state, then what happens to the statistics of the line? Okay? If you add up several Poisson distributions, what do you think will happen? I already sort of talked about it in the class, but you can think about it yourself. Okay? Before I finish, this is the last thing I'm going to write, is once again, you know the property of the Poisson distribution is as n increases, that is, as the average value increases, the ratio of the average value to the variance or to the standard deviation increases, right? So signal to noise increases as square root of n, right? This is the well-known short noise limit. That is that if you want a higher signal, that is, this is the signal, this is the noise, right? If you want this to be large, then you increase the average value n. Okay, this is the well-known result. As long as you keep turning up the laser power, you get better and better signal. This is noise, signal to noise ratio. Okay, this can also be seen. This is a reduction in the noise. Can also be seen from that quadrature representation that I had just sketched for you guys. Okay, so again, if you look at x and p, this is just as you make this larger and larger and larger. Let's say out here, you have the blob. The blob, of course, doesn't change its size. It's always half. but you can see that the ratio of this uncertainty, right, the ratio of the blob to the mean value, which is the length of this stick, which is the magnitude of alpha, is going to keep decreasing. Okay, this blob diameter is always fixed, it's half, right, as we saw. Okay, delta x, delta p is always 1/4. So the sort of the fuzziness in this blob is basically going to get smaller and smaller as a ratio to the length of that stick, which is the length of the stick is the magnitude of the electromagnetic field. And so this is why as you keep increasing the magnitude of the electromagnetic field, increasing the laser power, then the ratios of the uncertainty or the signal to noise ratio goes up. Okay. All right, I'll end there. In the next class, we will discuss squeeze states of light. Okay.